Hi, today I'm talking about bidimensionality. The prelims to study the problem I'll classify these as two prelims. First one is the easy ones which you'll already know, and the other ones which need some extensive proofs and studying. So we'll discuss these in detail, and this we'll rush through. Win-win approaches, the name suggests, we'll discuss later. So vertex subset problems, edge subset problems, phi minimization and maximization. What we mean by OPT, contraction closeness, minor closeness. We discuss it in the class itself. Grid T is a type of graph. Gamma T, it's also a type of graph. So win-win approaches, as the name suggests, it's a approach which results in a victory always. So tree width is a win-win approach. So studying problems with respect to a tree width is a win-win approach. Why so? Let's discuss. So suppose you have a good tree decomposition of the input graph. So intuitively we say that if you have a smaller tree width, for a lot of problems we can define a dynamic programming because you can intuitively see that a smaller tree width means it's very close to a tree structure, and trees we can solve a lot of decision problems by a simple dynamic programming. Like vertex cover, we can solve it in 2 power order t n power order 1, and a feedback vertex X similarly we can solve. Dominating set we can solve in the same complexity using a dynamic programming. Also we can solve scatter set using the same similar DP on tree width. Smaller tree width is a win, and a larger tree width is also a win. How so? Because a larger tree width will mean that the graph is very dense. So a dense graph is supposed to have a structure. So this structure or an obstacle which is making it difficult to be close to a tree can help us reduce a no instance, or in some cases yes instance, or in some cases give a reduction. So how no instance? Let's say we have a vertex cover where the tree width is greater than k. I can directly give a no instance because it's a minimization problem. For longest path, we can say if tree width is greater than k, we can give a yes instance because it's a maximization problem. Similarly, for longest cycle, a reduction is basically you can observe some set of edges in this minor, and you can say, okay, these edges are not at all of help to my solution, and reduce the instance to a smaller instance and apply this iteratively. We also consider this as a statement which we took, that tree width is minor closed. That is, given a minor of g, the value of tree width of h is less than equal to tree width of g. Okay. Now we'll define vertex subset problems or edge subset problems. Given a graph G and a parameter K, we have a statement phi gs which takes an input as G and S, where S is a vertex subset or edge subset depending on the type of these two problems. So for minimization, we can define cardinality of S to be less than equal to some k, and for maximization, we can define it to be greater than equal to some k. So this is trivial stuff. Similarly, 5 minimization, 5 maximization problems are defined as given a graph G and a parameter k, and you have to decide whether there exists a subset of vertices. You can take edges if it is a vertex edge subset problem, and you have to decide and the problem belongs to the instance belongs to the problem, that is gs is true for phi, and for a minimization problem you have to minimize the cardinality of given s, and for maximization you have to maximize, or it should be greater than equal to k for a feasibility or decision problem. Next, we'll define the notion of OPT, which all of us already know, but for the sake of argument, we tell that it is the minimum such k such that g of k such that phi g of k is true for a minimization problem, and for a maximization problem it's argmax k such that g of k is true for phi g of k is true. Trivially, if there is no such k that satisfies that belongs such that g of k belongs to q, or g of k satisfy phi, then we assign it plus infinity and assign it minus infinity. Although algorithmically we study the problem and we give it let's say n plus 1 or n square value for vertex cover or something. So it need not be infinity, it can be just an arbitrarily large value which cannot be something of a feasible solution, of the size of a feasible solution. Next we define contraction closed. We already know minor closed from the lecture slides or from the lectures. So minor closed is what we define as that. What is a minor? It is a sequence of edge contractions, edge deletions, vertex deletions on a graph G. We obtain a graph H, then H is called a minor of G. So minor closeness is when the optimal value of H in the given problem is less than equal to optimal value of G for the given problem for all minors of G and for all graphs G that are valid instances inputs to the problem Q. Similarly, contraction, I'll define contraction first. So contraction is a subset of the operations of a minor. So we define only one operation, which is edge contraction. So every edge which is derived from a series of edge contractions from G, original graph G, is called a contraction of G. So for the contraction closeness says for every contraction h of G, optimal value of H in Q for Q is less than equal to optimal value of G for all such G that are valid instances to Q. So we note that these two properties are the properties of a problem, not a graphs, or not property of contractions on minors. It's a property on Q. Next, we define a grid T as a graph. So intuitively, it's a graph of in a Cartesian coordinate 1 to t cross 1 to t and made of horizontal and vertical axis lines. So like this is grid 2, this is grid 3, this is grid 4. Formally, the vertex set is xy belongs to the Cartesian product 1 to t, and it has t square vertices. So and there is an edge between 2 points 1 and 2 if and only if L1 norm of 1 2 is 1. That is they are at a one distance at horizontal or one distance at a vertical alignment from each other. Next, we take this as a black box result only. Tree width is at most t. In fact, we'll take tree width is equal to t for gamma t. So why we are taking it as a black box? Because the result is as follows. It considers Cij's, which are basically crosses. So what is a cross? It is a set of edges, or it is a subgraph like this with the ith row and ith column and jth column and ith row. So it is a subgraph, and it says that the set of crosses form a bramble. So bramble is out of our scope for now. So we just take it as a black box that tree width of grid T is equal to T. Next, we define gamma T as a edge extend with some edge additions to grid T. So how do we add edges? So this is the simple way. So what we do, we take grid T and we add these diagonals top right to bottom left, and we choose this bottommost right vertex, apex vertex, and connect it to all the boundary vertices. Now this is gamma 3. Similarly, this is gamma 4. So one thing I'll like to mention that since tree width is minor closed and tree width, so anything which is minor closed will be contraction closed. It's easier to see because contraction is contraction is a subset of minor. That if something is formed as a contractions, then it is obviously a minor. So so gamma t is a grid T is a contraction of gamma T. So we know that tree width of grid T is greater than equal to T. Actually, it's equal to T. So we can claim that because of contraction closeness or minor closeness, tree width of gamma T is greater than equal to T. Next, we move on to the main part of our problem. So it's excluded grid theorem. So intuitively, the problem which we started with was say the graph is very complex or very dense. That is, it has a very large tree width. So we want to say that this has a structured obstacle, that is this has some graph as its minor or some graph as its contraction. So what excluded grid theorem says that if tree width of given graph G is greater than equal to some gt, where we'll define gt later on. If it is greater than equal to some gt, then we can claim that it has a grid T as its minor. Fine. So what is gt? gt is the best result till now is order T power 98 plus order 1, but this problem started with the study started by Robertson and Seymour, and at that point they gave this loose bound, but now further studies gave order T power 98. So also the results include a randomized polynomial time algorithm which either constructs a grid T or constructs a tree decomposition of tree width less than equal to gt. Fine. So we'll take all these as black boxes. So let's apply the grid theorem to a problem of cycle packing. So what is cycle packing? It asks or decides whether there exist greater than equal to k vertex disjoint cycles, like a graph like this. Graph like this will have one vertex disjoint cycle, which is any one of these cycles. You can choose this one also, you can choose this one also, but you cannot choose more than one. So this is cycle packing problem. It's a maximization problem. So now we now we consider a grid T and problem cycle packing on grid T. So what you can see is that if you look at all 2 by 2, all such 2 by 2 subgraphs, and you can have t square by 4 of these, you can say that it has at least t square by 4 vertex disjoint cycles, because all of these are 4 length C4s. So this is what we'll be using. So we'll say so you say you have a graph G whose size whose tree width is larger than g of t, where g is borrowed from the previous theorem. So if so it will have a grid T as its minor, and grid T will have greater than equal to t square by 4 vertex disjoint cycles. Minor closeness tells us that G will also have t square by 4 vertex disjoint cycles greater than equal to t square by 4 vertex disjoint cycles. So now we can say that if k is less than t square by 4, that is yeah, so if k is less than t square by 4, then less than equal to t square by 4, then we have a trivial yes instance, because the number of cycles is already more than k. So now we define a approximation algorithm. So this approximation algorithm has already been discussed in our lecture on the tree width. So what this algorithm does, it takes an input as gt, which is the desired tree width for our graph G, and it either approximately gives a tree decomposition with approximated tree width, that is gt plus 4. It gives a tree decomposition of width at most gt plus 4 times gt plus 4, or it says that its tree width is greater than gt, which implies it will have greater than equal to k vertex disjoint cycles, which we discussed earlier. So this is already a yes instance, and we can run a simple dp to find the cycles in this tree decomposition and give a yes or no instance accordingly. So this is how we used excluded grid theorem on cycle packing problem for a simple maximization problem, and gave a parameterized algorithm for FPT for cycle packing problem with respect to the parameter k. Next, we'll consider an extension to excluded grid theorem, which is planar excluded grid theorem. So I'll move through it fastly because I'll not be discussing the proof of this. So it's just that if the graph is planar in the previous theorem, we'll have GT as linear 90 by 2. That is, every graph of tree width greater than GT will have a grid T as minor. Now, one important constructive proof which this theorem gives is that you can have a order n square algorithm which approximately which does the following: either it gives a tree width approximated 9 by 2 plus epsilon t, a tree decomposition of a graph G with at most this, or it gives a minor model of grid T. So note that constructing a minor model of grid T in G clearly it shows that so what is a minor model? You have a mapping from a vertex of grid T or a minor to a subset of G, some subsets of G. So so it basically means constructing the grid T and saying that it's formed from a series of edge deletions, vertex deletions, or edge contractions from G. So this algorithm will be using in further proofs. Simple corollary from the previous algorithm that tree width of n vertex planar graph is less than n 9 by 2 square root of n plus 1 c. So we'll prove this as follows. Consider grid T to be the largest minor grid of G. That is, grid T plus 1 is not a minor of G. That is, for this to happen, we have to have the tree width of G to be strictly less than 9 by 2 into T plus 1. If it is greater than this, then using the previous algorithm, previous theorem, we can claim that tree width is greater than or equal to 9T plus 1. So we say that grid has T square number of vertices. Clearly, trivially, G will also have minimum T square number of vertices. So we can say that T is less than or equal to square root of n. And which means that tree width of G is strictly less than 9 by 2 square root of n square root of n plus 1. Okay, so I can write this as square root of n plus 1 c. Another result of this corollary is an algorithm which approximately builds a tree decomposition with the approximated tree width at most this, and it runs in order n square time. It's using the same argument. We'll not discuss it in details. Next, we again give another extension for planar excluded grid theorems for edge contractions only. Earlier it was minus, now we consider contraction. So contraction, the assumptions are it should be connected, and planar is already an assumption. So we get a GT of 90 plus 5. And similarly we get a constructive proof. We give an algorithm which builds a tree decomposition of width at most approximated tree width 9 plus epsilon t plus 5, and it gives a grid. It gives a gamma t as its contraction. Okay, so this theorem says that if a graph G has a tree width G greater than GT, where GT is defined as 90 plus 5, we claim that gamma t is a contraction of G. So I'll just give a sketch of the proof. I'll not be proving it totally. So how it follows is, so you can see that this GT, for this GT, I can have a 2t plus 1, that is t dash is equal to 2t plus 1, such that grid t dash is a minor of G. just plug in d dash and find, we can see that it's greater than equal to 90 plus 5. So we say that we have a grid of size almost 2t plus 1. First we'll claim that since the graph is connected, we'll have some diagonals here, because grid is anyway, minor is anyway obtained from some deletion of edges and vertices and edge contraction. So now the proof, what the proof does is it builds a gamma t from of dimension t by t from this almost 4 times bigger grid by some operations which we'll not be discussing in detail, but it builds it and thus proving the argument. Next, the main problem which we'll be discussing today is a bidimensional problem. So what is a bidimensional problem? We will define it for vertex subset problem Q. So it is bidimensional if it is contraction closed, and if the optimal value of Q given instance gamma t is bounded, lower bounded by some c times some constant time t square. Note that c should be greater than 0, like trivial, it should be greater than 0. So with these two assumptions we prove a theorem which is a parameter tree width bound on bidimensional problems. Note that for now we take it as contraction close, but you can also define, extend it to minor closeness, which we'll do by the end of this lecture. So the theorem is, if the Q is bidimensional problem, then we can claim that. So any of these theorems will have a the first part which is existential part, and the second is a constructive part which gives an algorithm approximating or also in deterministically finding the solution of a tree width given a bound. So the first part is says that the tree width of a G of a bidimensional problem is less than equal to some alpha times optimal value of G. So this alpha, you should note that it totally depends on the problem Q. It doesn't depend upon G. It totally depends on Q. So it can be considered as a constant. And the second argument says that there is a polynomial term algorithm which gives us a tree decomposition of tree width at most alpha times root of optimal value of G. So let's prove this parameter tree width bound theorem by taking in as black box the planar excluded grid theorem for edge contraction. So intuitively we'll map the first existential argument to our existential argument, and the second algorithmic argument to our algorithmic argument. So the proof is as follows. So we'll say let gamma t be the largest, be the largest contraction of G, that is gamma t plus 1 or any further bigger gamma is not a contraction of G. So we can use the first thing that tree width of G should be strictly less than G of t plus 1, and G is 9 by 2, sorry 9 times, it's for contraction, so it's 9 times t plus 5, so t plus 1 plus 5, so it is basically 9t plus 14, which is less than 23t. Because t is greater than 1, we can take it without any loss of generality. So we get that the tree width is less than 23t, and we can have a bound on t. T is greater than tree width, strictly greater than tree width of G by 23. So now see the first assumption of bidimensionality, that is which is contraction closeness, says that optimal solution of G for the problem Q is greater than equal to optimal solution of its contraction gamma t, which is greater than equal to which follows and it follows from the second assumption that this value is greater than some ct square for some c greater than 0 for all t greater than 0. So we have a lower bound on this. Now we say that t square now we plug in the value of t from this, which is c tree width square, tree width of g square 23 square. And if you see that if you take alpha 1 by alpha square to be c by 23 square, you will prove that tree width of g is less than equal to some alpha times optimal value of g का square root. So this concludes our first part proof. And so we'll use the first part of the proof and the constructive argument from planar excluded graph theorem for the second part. Second part is simply designing an algorithm. So I'll input to the graph epsilon is equal to so it's a black box. So I'll input epsilon is equal to 1, alpha is equal to 24 by root of c to the problem with t dash, where t dash is the same t which you are deciding the tree width on, t dash as 1 to t. So I'll run it for t times, not exactly t times, but I'll halt at a point where gamma t double dash basically gamma t dash is given as an output. So what this algorithm does, what was this algorithm doing, let's recall. So this algorithm either gave us a tree decomposition of tree width at most approximated 9 epsilon t plus 5, or it gave us minor gamma t dash of the minor, not minor, contraction of the given graph, which is gamma d dash. So we'll stop at a point where gamma d dash is obtained as a contraction. So as we know that from previous first part that for this t dash is equal to t, the tree width of graph is less than equal to alpha times OPTG. So we can extend it to the argument that for t dash less than t, the same thing follows. So the tree width, the maximum tree width of the tree decomposition we get, we return that, and we halt at a point where gamma t dash is returned instead of tree decomposition. So we know that we'll end up in having a tree width of tree decomposition with a tree width less than equal to gamma optimal value of g, and it runs in order n square times t. So it's again a polynomial in n square and t. So this is our algorithm. Next we prove an important theorem, which is BP theorem. I'll name it as BP theorem for the convenience of proof. So what are the assumptions? There are two assumptions. First is the problem is bidimensional. Second is provided with a tree width of t and a corresponding tree decomposition, provided with a tree decomposition of width t. We cannot say that tree width is t. Tree width is at least we can say that tree width is at most t, because it's the minimum of all tree widths of tree decompositions. So we have given a tree decomposition of width t. It can be solved in FPT in 2 power order t and per order. Note that however we can extend this 2 power order t to k power order k, sorry not k, t power order t poly n, and the subsequent result will change accordingly. It will be t power order root t and power order 1. So given these assumptions that it can be solved with the for the given width tree decomposition, with tree decomposition and bidimensionality, we say that it is FPT with running time 2 power order root k poly n on connected planar graphs. So it's very amazing to see that given a bidimensional problem and just an existence of an algorithm that computes FPT with respect to tree width and the corresponding tree decomposition, we can give a FPT with respect to kn. It's very interesting to see. Okay, so we now give the proof of BP theorem, taking in the black box as parameter tree width bound and specifically the algorithm constructive part of the algorithm. theorem. So we say that we can construct a tree with tree decomposition of graph G, where the width of the tree is less than equal to alpha times optimal value of G. We are omitting Q for the sake of convenience. So alpha is totally a function of Q. It doesn't depend upon G. So we have this. So consider the first case where given this tree width, it's less than alpha times root k. Oh sorry, if it is greater than equal to alpha times root k, this means optimal value of G is greater than equal to k, which means it is a yes instance given a maximization problem, and it is a no instance given a minimization problem, and we are happy we have 1 if the first case is there. So trivially we'll take the second case, which is tree width is less than alpha times root k. So I can say that approximately I have a tree width, I have a tree decomposition which is of tree width alpha times root k or less than that. So I'm happy because now here comes the assumption from second assumption. So this all we did with the first assumption itself, that it is BP, that it is bidimensional. Now the second assumption comes into play. Given a tree decomposition of width at most this, I can run it in order time 2 power order alpha root k poly n and find a solution. So alpha is a constant which gives us 2 power order root k and power order 1 algorithm, which is an FPT, and this concludes our result. Again I'll say note that if you take this 2 power order k, this as k power order k, then you will get a resulting solution as k power order root k 1 power order 1. So it's not difficult to see that the function is mapped to similar thing and we can extend it to other FPD functions also, not only sub exponential. Okay, so the proof is done. We'll now okay, so the biggest assumption here was connected planar graphs in BP theorems. So why connected? Okay, I'll say why connected is there, because we have used planar excluded grid theorem, which had this assumption of connectedness. And intuitively, why we had this assumption? Because we sort of building gamma t from a grid of almost double size. So we sort of had to take assumption that the graph is connected, or else we will not have this gamma. We cannot construct this gamma t from grid t such that gamma t is a contraction of the original graph. So we had this connectedness carried along all the theorems which were derived from this. So but we can say that we can relax this connectivity property or connectivity requirement in one case, where the problems which are monotone under removal of connected components. So what do you mean by monotone? Monotone means it's like it's similar to Meinl closed and contraction closed, that if you remove a component from the graph, its optimal solution still remains the same. So you can clearly see that vertex cover, feedback vertex set, dominating set, dominating set are all monotone under removal of connected components, because removing some edges, some components doesn't increase the vertex cover, similar for feedback vertex and dominating set. So we can relax this connectivity assumption given the problem is monotone. So next we'll move on to the intuition of why we define bidimensionality, because okay, why we define bidimensionality, why we only define, like why is that we are defining a whole class of problems for taking assumptions like the optimal solution size of gamma t should be some ct square greater than equal to some ct square. So why are we doing is that because a great class of number of problems belong to this class, and we can have a simple mechanism for the problems. So I'll consider planar vertex cover, which is vertex cover on planar graphs, and use planar extended grid theorem on minors to find an FPT with respect to k. not with respect to tree width, with respect to k. So we see that for the problem to for the proof, we need three properties for the from the vertex cover. So first one is lower size on the size of the vertex cover of grid T, and I'll say it's greater than equal to T square by 2. Why? Because see, this is a grid. I can give you a constructive proof that consider this matching. This matching is of size sorry, this is not there. Consider this matching, it's of size at most T square by 2, and you know that vertex cover is at least the matching. So we know that T square by 2 is the minimum size of the vertex cover for a grid T. Another assumption is that it should be is it solvable for a given tree decomposition of a T. So we already know that we have a simple dp of 2 power order T poly for vertex cover given a tree decomposition of a T. Another property is that we consider minor closeness of the vertex cover. Okay, so it is we'll give this algorithm as follows. If TC, observe that if T is greater than square root of 2k plus 2 greater than equal to, we can say that the grid T itself will have a vertex cover of size greater than equal to T square by 2, which is greater than equal to k plus 1, which is a no instance. So we can directly give a no instance. So let's take the case when T is equal to square root of 2k plus 2. So we can use the constructive part of the planar excluded grid theorem, which says that it will either construct a tree decomposition of width g of width at most 9 by 2 plus epsilon t, or it can conclude that g has a t as a minor. So how we can use this is that for the first part we can design a simple dp for the algorithm and compute it in some fpt of k, which is basically 2 power order t n power order 1, where we know that t is square root of 2k plus 1, so it becomes 2 power order square root of k n power order 1, and or we can conclude that g has a t as a minor, and we can say that it's a no instance. So again, it's a win-win approach. So what we got from this was that we have observed that it can be this property system can be could be generalized to a lot of problems like longest path, longest cycle, and it could be used to get FPTs with respect to K. So what these properties were in a generalized version, that you have a, if given that you have a bound on the size of the solution of a grid T, sorry it's a typo, it should be grid T, and the bound is of the form omega T square, and you have a FPT running in time 2 power order T poly n, given a tree decomposition of width T, and the problem is minor monotone, or the problem is contraction monotone or contraction closed. So this we consider contraction monotone for bidimensionality for now. So this intuition is what made us define bidimensional problems, and the theorem of the two theorems, BP theorem and parameterized tree width bound. So this is the intuition which led to the proof, or led to the definition of bidimensionality. So we'll now also give some corollary of both the theorems. So the BP theorem can be used to derive FPT algorithms in running in time 2 power order root k n power order 1 for the following problems. Planar vertex cover, we know that it is a bidimensional problem, and it is monotone under connectedness. So planar independent set same, planar dominating set same. So scattered set we'll discuss. So I'll not discuss, but I'll just define what scatter set is, and I'll leave it for the proof that a scatter set is also has a dp running in time 2 power order t n power order 1, And it is following all the assumptions which for the BP theorem. So scatter set is basically a set of vertices x, subset of vertices, such that every other vertex in this graph has the minimum distance, that is for all u and v belong to x, tuv should be greater than r. They are r distance apart. It's a scattered graph. Okay, and so induced matching, it's another problem. We can intuitively see that it's also FPT, and it also follows all the assumptions of BP theorem. So induced matching is basically given find an h as a subset of vertices such that mod h is less than equal to k, and such that g of h is itself a matching. So the induced graph on h is itself a matching. Sorry, it should be 2k. Anyway, it can be k, but formally it's defined as 2k. So g of h is a matching with k vertices. So g of h will have exactly k edges since it has 2k vertices. Next problem is R center problem. Again, the definition follows. It's basically find a subset x such that every other vertex in the edge so that every other vertex in the remaining graph is reachable to at least one vertex in the length less than equal to r. So note that here we are considering constant r. R is not one of the parameters, it's a constant. So these are all the problems which get a running time of 2 power order square root of k and poly for the given BP, for the given assumptions that considering the assumptions of the BP theorem. They all satisfy the assumptions of BP theorem. Again, corollary, which is based on parameter tree width bound theorem, and another theorem which is we will not discuss, theorem 7.10, which is basically theorem giving DP formulations for running in the order T power order T poly n given a tree decomposition of width T. So this all these problems are having a running time this. So as I already mentioned that BP theorem can be extended to plugged in with any function of T here, and we can have a corresponding function k power order root k, basically root k power order root k n power order 1, which gives this running time of for all these problems: planar vertex, feedback vertex at longest path, longest cycle, cycle packing, connected vertex cover, connected dominating set, connecting feedback vertex set. So connected vertex set cover is a vertex cover where the solution is connected. Similarly, dominating set and feedback vertex set. So this is derived from BP theorem. It's an extension to BP theorem that the function 2 power order T can be changed to T power order, basically can be changed to some f of T, and we will get some f of root k for the FPT f of root k corresponding to the parameter k. Okay, so the possible extensions are the planar excluded grid theorem has been generalized to H minor free graphs. What is an H minor free graph? The name suggests for a fixed H minor free graph is a set of graphs or a class of graphs whose minor is not H. So we define g of T as, okay, we define a equivalent version where we say that every H minor free graph G has a tree width more than alpha H times T, where alpha H directly depends on H, only depends on H, and it contains, if this is there, if tree width is greater than alpha HT, we have a grid T as minor. So we also extend it to apex minor free graphs. We can claim that for every apex minor free graph, the tree width of a given graph G is less than equal to alpha Q times optimal value of G. So what is an apex graph? First is a graph. We consider a planar graph and choose an apex and choose a set S. So subset S, arbitrary subset S of vertices. So we add edges from apex to this apex to all the vertices of this S, and we call the resulting graph as apex minor free graphs, apex graphs. So apex minor free graphs are what? Apex minor free graphs are graphs, class of graphs whose minor is not any apex graph. So the result that tree width is less than equal to this follows for apex minor free graphs, and it also can be extended. Bidimensionality can be extended to minor bidimensionality, like we discussed earlier, and this has been used to prove um, parameterized algorithms which are sub-exponential in time for general vertex cover and feedback vertex set. So that's all. Thank you. So the references, I guess it's the only the book on parameterized algorithms by Saket Saurabh. All the theorems have been derived and corollaries have been derived and taken from them. And all the images have been sourced from the book or from Google.